The navigation system is divided into three main groups: Air Data and Inertial Reference System, ADIRS, plus standby instruments, radio navigation, additional navigation systems. There are several subsystems within each group. The first group includes Air Data Inertial Reference Units, ADIRU, Global Positioning System, GPS, Standby Instruments. Let's concentrate on the radio navigation group. The radio navigation group includes radio navigation aids, radio altimeters, digital distance and radio magnetic indicator, DDRMI. The additional navigation systems include Ground Proximity Warning System, GPWS, or Enhanced Ground Proximity Warning System, EGPWS, ATC transponders, weather radar. This completes the introduction to the subjects that will be covered in the following modules. The purpose of the Air Data Inertial Reference System ADIRS is to provide air data and inertial information to the EFIS system, the FMGC, and other users. The A320 is equipped with three separate but identical Air Data Inertial Reference Units. Each ADIRU combines an Air Data Reference Computer, or ADR, and a Laser Gyro Inertial Reference System, or IR. The ADR and IR systems of each ADIRU operate independently, and failure of one system will not cause failure of the other. The ADR part receives information from aircraft probes and sensors. The ADR part provides various items of air data to the Flight Management and Guidance Computers, FMGC, and other users. The air data provided includes Mach, airspeed, temperature, overspeed warnings, barometric altitude, and angle of attack. The IR part provides inertial data to the FMGC, EFIS, and other users. The inertial data provided includes track, heading, acceleration, flight path vector, aircraft position, ground speed, and attitude. The three ADIRS are controlled through the ADIRS panel, located on the overhead panel. They are initialized through the two MCDUs located on the pedestal and by two of the switches on the switching panel located at the front of the pedestal. Independent data is supplied by each ADIRU. Let's see an example of this. In the EFIS system, ADIRU 1 supplies the captain's EFIS and ADIRU 2 supplies the first officer's EFIS. ADIRU 3 is available as a backup to either EFIS system via the switching panel. Use of the switching panel will be covered in the abnormal section. Now let's look at the ADIRS control display unit. The panel is divided into two parts, the upper section for the IR and the lower section for the ADR. The three rotary mode selectors have control over both the IR and the ADR. The controls and indicators for the individual ADRUs are grouped and arranged in the following order: 1, 3 and 2. Each ADRU has an associated IRS rotary mode selector. In the off position, the ADRU is not energized, so ADR and IR data is not available. In the navigation position, the ADRs are energized. The navigation position is the normal mode of operation, and full inertial data is provided to the aircraft systems. The on-bat light illuminates to inform the crew that the ADRU system is being powered by aircraft batteries only. The light also illuminates for a few seconds at the beginning of a full alignment as a test of the battery circuit. We will discuss this further in the normal and abnormal operation modules. Each inertial reference unit has an associated indicator. The align light illuminates steady white when the respective IRU is operating normally in align sequence mode. The align light flashes white if there is an IRU alignment fault, no present position entry has been made after 10 minutes, the difference between the position at shutdown and the entered position exceeds 1 degree of latitude or longitude. Present position information for ADR's alignment is normally entered via the init page of the MCDU. This method will be explained in the normal operation module. The type of information displayed is selected with the data selector. The system selector enables the crew to switch the display off or select one of the 3 ADRUs for display. We select System 3 for you. Notice that the display now contains the present position or PPOS information for ADRU 3. The wind position indicates the true wind direction and wind speed. The heading position indicates the true heading. With heading selected during IRS alignment, the time remaining until alignment is complete is displayed. This is shown by a TTN, time to navigation indication. The duration is approximately 10 minutes, but it can increase with the aircraft latitude. The status position displays IRU status and guidance to the pilot in abnormal situations. For example, the current display is showing Enter PPOS, asking you to enter the present position of the aircraft. The track and ground speed position indicates the true track and ground speed of the aircraft. The spring-loaded test position tests the lights on the keyboard and produces a test pattern in the main display, as shown. The keyboard is a standby facility, allowing, for example, entry of present position for alignment of the IRS. You will see an example of the keyboard use in the abnormal operation. The following items can also be used in case of given failures. The AT position of the ADRS selectors allows the selection of this IR mode, providing only heading and attitude information in case of loss of navigation capability. The 3 ADR switches normally remain on, but they can be selected off in response to ECAM procedures. When done, it only stops the ADRs, not the IRs. We will discuss these in the abnormal operation modules. The radio navigation aids enable the crew to navigate and monitor the position of the aircraft. The A320 family is equipped with 2 VORs, 2 DMEs, 2 ILSs, 2 ADFs. The FMGCs can automatically tune the VORs, DMEs and ILSs for position updating and display purposes. Note, the ADFs are auto-tuned by the FMGCs only in specific circumstances. The radio navigation itself is controlled by both FMGCs and can be monitored through MCDU pages. Via the radio navigation page, either MCDU enables the crew to manually tune a specific nav aid, including both ADFs. FMGC auto-tuning continues normally in the background. Note that when an ILS approach is selected, ILS-1 is displayed on PFD-1 and ND-2, ILS-2 is displayed on PFD-2 and ND-1. As you have seen in the EFIS chapter, the mode selector enables the pilot to select different ND modes to display flight plan and NavAids data. Plan mode is recommended when entering and checking the flight plan. However, notice that NavAid data cannot be displayed in this mode. In all the other modes, ROSE ILS, ROSE VOR, ROSE Navigation and ARC modes, the NavAids can be displayed provided the ADF VOR selectors have been switched to VOR or ADF position. Here, as an example, the ROSE VOR mode with ADF-1 and VOR-2 selected. ADFs are shown as green pointers, here ADF-1. VORs are white pointers, in this example VOR-2. Note also that the receiver 1 data is displayed on the left side of the ND and the receiver 2 data on the right side. The associated NavAid data is displayed at the bottom of the ND in their respective colors and sides. We will see the different ND modes and NavAid tuning in more detail in the normal operation module. In the unlikely event of a double FMGC failure, the backup tuning mode provides radio navigation redundancy to the crew. The backup tuning mode is accessed via the Radio Management Panel's RMP. Note, RMP3 has no backup tuning capability. For NavAid tuning, RMP1 standby navigation keys are associated with VOR DME1 and ADF1, while RMP2 keys are associated with VOR DME2 and ADF2. The ILS keys are slightly different. The ILS frequency tuned on either RMP is sent to both ILSs. To access the backup tuning mode, the navigation key has to be pressed. When the backup tuning mode is selected, i.e. navigation key illuminated, the control of the associated receivers is transferred to the RMP, and the NavAid tuning capability of both FMGCs is lost. This is indicated on the MCDU by a change on the radio navigation page, which now shows only the titles. To return the control to the FMGC, the navigation key has to be pressed again. In backup tuning mode, the selection of one of the standby navigation keys enables the crew to tune the associated nav aid. We will see how to operate them in the abnormal operation module. We will now study the Digital Distance and Radiomagnetic Indicator, DDRMI. The DDRMI is fitted on the main panel. The DDRMI displays ADF, VOR and DME raw data and combines a traditional RMI and bearing pointer presentation. Two bearing pointers are provided, each with a different distinguishable shape. Each can display either VOR or ADF information. Each pointer has an associated control knob. The left knob selects either VOR1 or ADF1. The right knob selects VOR2 or ADF2. Here, VOR1 and VOR2 are selected. The compass card displays the bearing as supplied by ADRU1. The counters indicate the DME distance. However, the window will display only dashes if an ADF is selected. Here, ADF2 is selected. The A320 family can be equipped with an enhanced ground proximity warning system, EGPWS. We will first discuss the standard ground proximity warning system functions and then present the enhanced ground proximity warning system particularities. The purpose of the ground proximity warning system is to enhance safety by alerting the crew to potentially hazardous situations involving terrain collision or incorrect landing configuration. The ground proximity warning system monitors the aircraft flight path and generates visual and audio warnings, alerts, when the aircraft is in one of the defined hazardous situations. These warnings will be overridden by stall or wind shear warnings. The ground proximity warning system processes the data from RA1, ADIRS1, ILS1, FMGC1, LGCIU1. Failures of these units will be studied in the abnormal operation modules. Most ground proximity warning system alerts and warnings are generated as a result of changes in radar altimeter heights or the rates of those changes. The system predicts potential hazards from these trends, but has no forward-looking capability. Therefore, impact with a near vertical cliff face cannot be predicted. Ground proximity warning system does not absolve the crew from monitoring aircraft position and safety altitude. The ground proximity warning system control panel is located on the left side of the overhead panel. Ground proximity warning system visual warnings are provided on the miscellaneous panels. The system can be tested by pressing either ground proximity warning system glide slope push button switch. This test is normally performed by the maintenance crew. In addition, two loudspeakers located on each lower side of the main panel broadcast ground proximity warning system aural warnings, even if they are turned off. Ground proximity warning system enhances safety by warning the crew of potentially hazardous situations during flight at low heights. Crews should react to any ground proximity warning system warning immediately without attempting to assess its validity. Ground proximity warning system operation is fully automatic in the normal lights out configuration. We will now study the aural and visual alerts and warnings. But if a high rate of descent is detected at low level, ground proximity warning system will generate an aural repeated sink rate alert. If this rate is or becomes excessive, the repetitive aural warning whoop whoop pull up will be generated. In both cases, the red ground proximity warning system lights will illuminate. If rising ground is detected as a potential threat to the safety of the aircraft, ground proximity warning system will alert the crew with a repeated terrain aural alert. The system will generate a whoop whoop pull up warning after the terrain alert has been repeated twice. The red ground proximity warning system lights will illuminate in either case. If ground proximity warning system detects a rate of descent during the initial climb after takeoff or following a go-around, it will give a repeated "Don't sink" alert with accompanying ground proximity warning system red lights. If the landing gear and flaps are retracted, and ground proximity warning system detects that the aircraft is close to the ground, it generates a too low terrain aural warning, and the ground proximity warning system red lights illuminate. At very low levels, the aural warning too low gear would be generated if the landing gear is still retracted. If the landing gear is down, but the flaps are not in landing configuration, the warning is too low flaps. Note that the too low gear warning has priority over the too low flaps.
Quite slow.
Below approximately 1,000 feet on an approach, a ground proximity warning system glide slope aural and visual alert will be generated if the runway is ILS equipped, the ILS is tuned, the ILS signal is valid, the aircraft is significantly below the glide slope. Both amber glide slope lights will illuminate.
Quite slow.
The aural message will become louder to indicate a warning if no corrective action is taken as the aircraft gets closer to the ground or if it descends further below the glide slope. Note that some airports around the world have approaches and departures which are not compatible with standard ground proximity warning system operation. These airports are programmed into the ground proximity warning system database, and the warning thresholds are modified to avoid nuisance warnings. The ground proximity warning system panel allows the crew to inhibit some warnings. Flap 3 is a recognized landing configuration. If the option is used or if required by an ECAM procedure, the crew should select Landing Flap 3 push-button switch on to ensure that the ground proximity warning system does not generate warnings when it detects that the aircraft is not in the full flap configuration. The associated green ground proximity warning system Flap 3 memo message is displayed on the engine warning display. Following certain failures, a landing may have to be made with a reduced flap setting. The crew can select the flap mode push-button switch off to inhibit ground proximity warning system flap warnings. If the flap mode is off, the green flap mode off message is displayed on the engine warning display. When selected off, the glide slope mode push-button switch will inhibit the ground proximity warning system glide slope warning. The white off light illuminates when the ground proximity warning system is selected off. All warnings are inhibited. If your aircraft is equipped with the Enhanced Ground Proximity Warning System, EGPWS, a forward-looking capability for terrain is added. The basic functions we have just studied remain unchanged. Enhanced Ground Proximity Warning System is based on terrain database and FMGC current position, not on radar returns. The purpose of the Enhanced Ground Proximity Warning System is to avoid a controlled flight into terrain and to give enough time to the crew to perform an avoidance maneuver. The terrain information is displayed on the ND except in plan mode. A different image texture, an image display which sweeps from center outward to both ND sides, and a tear indication instead of the radar tilt indication help the crew to make the difference between the Enhanced Ground Proximity Warning System terrain computed data and the ground picture sensed by the radar. The terrain elevation surrounding the aircraft is color-coded. Two tear-on ND push-button switches are fitted on each side of the main panel. To display the terrain picture on his ND, a pilot will have to switch on his respective tear-on ND push-button switch. Note that the weather radar information is replaced even if it is switched on. In the lights out position, the Enhanced Ground Proximity Warning System operation is fully automatic. The tear push-button switch in the off position allows the crew to inhibit the enhanced functions, but keeps the basic Ground Proximity Warning System functions operative. In case of failure of the enhanced functions, the fault light comes on, but the basic Ground Proximity Warning System functions remain operative. As for the basic Ground Proximity Warning System, the system push-button switch controls the basic functions. The Enhanced Ground Proximity Warning System uses a terrain database coupled with an FMGS position to calculate two terrain envelopes ahead of the aircraft. When a conflict is detected between these terrain envelopes and the terrain memorized in the database, an alert is triggered. One terrain envelope corresponds to a caution level, while the second one corresponds to a warning level. If the caution terrain envelope is penetrated, the areas which violate the caution envelope limits turn to a solid yellow color. An amber tear ahead message appears and a repeated terrain ahead oral alert is generated. If the terrain warning envelope is penetrated, the areas which violate the warning envelope turn to a solid red color. A red tear ahead message appears and a repeated terrain ahead pull up oral alert is generated. In both cases, the red ground proximity warning system lights will illuminate. As for the basic ground proximity warning system warnings, crews should react immediately without attempting to assess its validity. In case of caution or warning, if Tear On ND is not selected on, the terrain display is set automatically to on and the on light on the Tear On ND push-button switch comes on. The second Enhanced Ground Proximity Warning System protective function provides a terrain clearance floor envelope for each runway stored in the database. This function warns of a premature descent below this floor, regardless of aircraft configuration. Caution. The relative height is calculated using the Captain Barrow setting. Thus, the system does not protect against Barrow setting errors. The position is calculated using FM1. The system does not protect against FM1 position errors. When the aircraft position accuracy provided by the FMGS is low, the enhanced functions of the Enhanced Ground Proximity Warning System are automatically deselected. Tear Standby appears in green on the ECAM memo, and the terrain display is deselected until a high level of navigation accuracy is restored. The basic ground proximity warning system functions remain operative. Two radio altimeters are installed in the A320. They measure the aircraft height above the ground accurately. There are no radio altimeter controls in the cockpit. Both radio altimeters come on automatically when AC power is applied to the aircraft. After a brief self-test, the radio altimeters are in a standby mode during ground operations. They become active at liftoff and then operate continuously until touchdown. Radio height is always expressed as the number of feet between the bottom of the wheels and ground. Radio altimeter data is supplied to several different users and is displayed on both PFDs at all times below 2,500 feet above ground level. Normally, radio altimeter 1, RA1 height, is displayed on the captain's PFD and radio altimeter 2 on the first officer's PFD. The radio altitude display on the PFD changes in color and size based on height above ground and/or proximity to the decision height. This color-coded digital readout is coupled with a white ground indication line and a red ground ribbon on the altimeter scale. The ground indication line and the red ground ribbon correspond to the raising ground level when the aircraft is descending. As the aircraft descends below approximately 500 feet above ground level, the red ribbon appears at the bottom of the altimeter scale and begins to move up. The white ground line moves from the bottom of the PFD towards the horizon. At touchdown, the ribbon is in the center of the altitude readout, and the white ground line is merged with the horizon as shown. These are designed to be used as a ground reference during autoland operations. In addition to the visual indications during approach, there is a synthetic voice for radio height announcement. Depending on individual airline requirements, auto call-out announcements are made at predetermined radio altimeter heights. Example, 400 at 400 feet radio altitude. These callouts will be heard even if the loudspeakers are turned off. The A320 family is fitted with two ATC transponders, which provide responses, including altitude reporting, to radar interrogation. In normal operation, ADR1 provides barometric information to ATC1, ADR2 supplies ATC2. A Traffic Alert and Collision Avoidance System, TCAS, provides the crew with traffic information and warnings of potential conflicts, with avoidance instructions. TCAS can only detect and indicate other traffic which is equipped with a transponder. A control box located on the center pedestal allows pilot control of the ATC and TCAS systems.
The left part is dedicated to the transponder controls, while the right lower part is used for the TCAS controls.
A weather radar is installed to detect severe weather and display it on the ND for use as a severe weather avoidance tool. The weather radar control panel is located on the center pedestal. We will now look at the different controls and indications of the weather radar. The on-off switch controls the power supply. When switched on, the tilt indication appears on the ND. The tilt knob is used to adjust the radar antennae relative to the horizon. The tilt angle is displayed on the ND. The gain knob is used to adjust the sensitivity of the receiver manually. In this case, the word manual appears in green under the tilt indication. In the auto position, the radar adjusts the gain to the optimum setting automatically. And the three-position mode selector. Weather shows the intensity of precipitation. Weather turb shows the turbulence areas in magenta. Map. The radar operates in ground mapping mode. When auto is selected on the wind shear toggle switch, the predictive wind shear system generates the appropriate visual and oral annunciations. The tilt and gain are automatically controlled for the scanning. Note, in this mode, the tilt displayed on the ND indicates only the tilt value manually selected on the panel, not the real value of tilt. The A320 family is equipped with standby instruments which include a standby airspeed indicator, ASI, a standby altimeter, a standby horizon. Moreover, a standby compass is fitted on top of the windshield center post in a closed compartment. It may be pulled down for use. A deviation card is fitted above the compass. We will now have a closer look at the other instruments. The ASI is fitted with an airspeed pointer and airspeed bugs. The only pilot input to the ASI is the manual setting of the speed bugs. The standby altimeter is fitted with an altitude pointer, an altitude counter, a baroset counter which displays pressure setting in inches of hectograms or in hectopascals, depending on the option chosen, a baroset knob. The standby horizon is erected by pulling the caging knob. The standby horizon is the only standby instrument requiring an electrical supply. In the event of total electrical failure, it continues working for approximately 5 minutes. In case of instrument or power supply failure, a failure flag appears.
As part of your walk-around, you would verify the condition, damage, blockage of the 3 angle of attack AOA probes, the 2 captain and first officer static ports. Check that the static ports are clear and the covers are removed. The 3 pitot probes, the 2 standby static ports. Check that the static ports are clear and the covers are removed. The 2 total air temperature TAT probes, the radar radome and its latches, navigation antennas on the lower center fuselage. For normal operation, after AC power has been connected to the aircraft, ensure that the ADR push buttons are in their normal lights out position. Then, select the navigation position on the 3 IR mode selectors. The alignment process is now started. The on bat light illuminates amber for a few seconds as a test of the battery circuit, and the white align lights illuminate to indicate that alignment is in progress. Almost immediately, air data information is shown on both PFD. On the ECAM memo, the message IRS in align greater than 7 minutes appears. This message tells you that the alignment process has begun. It takes approximately 10 minutes for a full alignment, but the ECAM will only count down from 7 minutes. After approximately 30 seconds, attitude information is displayed on both PFDs. To allow an IRS alignment, you will have to enter the present position in the init page of the MCDU. To save time, we have already selected this page for you. One method of position entry is to insert a company route. We have inserted the company route, all care, into the scratchpad for you. It corresponds in this database to a flight from Paris-Orly to Cairo. Note, the other method is a city pair input via line select key 1 right. Line select this route to the company route field by selecting the 1 left key. As you can see, this has automatically entered the latitude and longitude position of Orly Airfield into the MCDU. This data has been obtained from the Aircraft Navigation Database. Notice the up and down arrows beside the LAT title. These arrows indicate that the latitude information can be adjusted by using the MCDU slew keys. Press the MCDU slew up key to change the latitude information. Notice that the latitude figure has been increased by 0.1 of a minute. Now to adjust the longitude position, line select for right. Notice that the 2 arrows have now moved across to be alongside the long title. The longitude information can be adjusted in a similar manner to the latitude. Press the MCDU slew down key to change the longitude information. Notice that the longitude has been decreased by 0.1 of a minute. Using this method, it is possible to fine-tune the position to, for example, the gate position. The IRS in Align message on the engine warning display counts down the time remaining until full alignment is completed. We have speeded up this countdown for you. If the position has not been inserted, the countdown will stop at 1 minute. In the MCDU scratch pad, a message, Enter Present Position, appears, and the Align lights on the ADIRS panel will begin to flash. Once IRS alignment is complete, all PFD and ND information is available. The IRS in Align message disappears from the engine warning display memo, and the ADIRS control panel Align lights extinguish. For the remainder of a normal flight, no further pilot input is required on the ADIRS system. Occasionally, during a turnaround, a residual ground speed can necessitate an IRS rapid realignment. Residual ground speed can be seen on the ND. ND1 shows the residual ground speed for IR1, while ND2 shows the residual ground speed for IR2. To see the residual ground speed for IR3, you can use the ADIRS panel. The system selector should be in position 3 and the data selector in the track ground speed position. To carry out a rapid alignment, the 3 mode selectors are momentarily switched off. Select IR1 mode selector to off. Now turn it back to navigation. Fast realignment is now in progress. Notice that all 3 Align lights have illuminated. You should note that if a rotary selector is switched to the off position for more than 5 seconds, a full alignment will commence, lasting up to 10 minutes. You now have to insert the position. A company route has been typed for you in the scratch pad. Please line select it to 1 left. With a position now in the MCDU, you can see that the Align IRS prompt has appeared on the MCDU display. After confirming that this is the correct position, it can be sent to the ADIRS. Line select 3 right to realign the ADIRS. The actual position has been sent to the ADIRS. The ADIRS will take approximately 3 minutes to realign to the position entered into the MCDU. Now, the ground speeds are all 0 and the rapid alignment is complete. The ADIRS are now aligned and the flight plan has been entered into the MCDU. Let's see the other operations you have to do concerning the navigation system in a normal flight. VOR1 pointer and data are shown on the ND. Display VOR2 data. The left side of the ND shows information from receiver 1 and the right side from receiver 2. Notice that a small picture of the associated pointer being used is represented close to the name of the corresponding VOR. As the VOR associated data and pointers are displayed, both receivers consider the VOR signal as valid. On the second line, the VOR identifier appears, here Bravo Tango. On the third line, in green, the DME distance in nautical miles. To see the nav aids automatically tuned by the FMGC, we have to call the radio navigation page. Call the radio navigation page. You can see on the radio navigation page that the FMGC has automatically tuned the VOR Bravo Tango on both receivers. Select VOR D key. The VOR DME present in the database are now displayed. We will manually select, as a training example, the VOR DME Mike Echo Lima. The VOR DME identifier MEL has been typed for you in the scratchpad of the MCDU. Insert it by selecting line key right 1. Insert it by clicking on line select key 1 right. Notice the VOR identifier in uppercase on the MCDU, indicating a manual selection. Notice also, as a valid signal is not yet received from VOR MEL, the associated data and pointer are not shown. Note, once the signal is received, the manual selection is confirmed by a tiny underlined M beside the VOR2 data location. Set ILS display on. Now, select ILS push-button switch. On the PFD, you can check the ILS identifier, Oscar Lima Echo. In this case, the frequency and the course. The course is also indicated on the ND. The check and the selection of the nav aids are now complete. We will carry on with the settings of the altimeters. We will now set the barometer settings on the EFIS control panel. The current QNH is 1007 hectopascals. Set the correct QNH on the EFIS panel. The new QNH is displayed on the EFIS control panel. On the PFD, the QNH is shown and the altitude indication can be checked. We will now assume that we have taken off. During the climb at transition altitude, here 4,000 feet QNH, the barometric indication will flash on the PFD. You will have to switch the barometric settings to standard, STD, by pulling the barometer reference selector. Set Baro Standard. Standard appears on the EFIS control panel. You can also see the standard indication on the PFD in cyan and yellow boxed. Notice also the selected altitude, which has changed to a flight level indication, flight level 130. Let's assume we have performed the same setting on the standby altimeter. As the VOR receiver 2 now receives a valid signal from the VOR MEL, the associated pointer and data are displayed on the ND. As MEL VOR is not equipped with a DME, the DME indication is replaced by green dashes. The indication Navigation Accuracy Upgrade has appeared at the bottom of the ND and in the MCDU scratchpad, meaning that the navigation accuracy level has automatically switched from low to high. We will see now how to make a navigation accuracy check. The objective of the navigation accuracy check is to compare the raw data from the tuned nav aids with the corresponding FM computed data. The SOP recommends to do this periodically in cruise, prior to initiating the descent and when entering a terminal approach area. If your aircraft is equipped with GPS primary, no accuracy check is required as long as GPS primary is available. The GPS mode can be checked on the progress page. If the GPS is no longer primary, the message GPS primary lost is displayed on the ND and in the MCDU scratchpad. Notice that the navigation accuracy level stays at high. Nevertheless, the navigation accuracy has to be verified. The SOP recommends in such a case to perform the comparison on an hourly basis. This check has to be performed whenever the following cases occur: IRS-only navigation, the progress page displays low accuracy, navigation accuracy downgrade message appears on the MCDU and on the ND. To perform this check, you have to use the selected nav aids and display them on the ND. We have set the ND range to 80. The VOR Sierra Papa Romeo has been manually tuned on receiver 1 and the VOR Papa Alpha Sierra on receiver 2. Note that the VOR Papa Alpha Sierra is the 2 waypoint of the flight plan. There are two ways to do this check. The first method is to compare the 2 waypoint distance and bearing, which is FM computed data, with the corresponding nav aid DME distance and bearing. Call the progress page. The second method is to insert a VOR DME ident in the Bearing Distance To field on the progress page, and to compare the computed bearing distance with the raw data on the ND. We have typed the VOR DME ident SPR in the scratchpad for you. Insert SPR in Bearing Distance field. We now have on the progress page the computed bearing and distance to the selected nav aid. The distances shown on the ND and on the progress page can be compared. The last method consists in checking that the raw data needle passes through the blue FMGS generated symbol for the VOR DME, and that the position of this symbol corresponds to the DME distance. Whatever method is used, if the error is less than 3 nautical miles, the check is positive and the FN position is reliable. The SOP recommends to use the ND in ARC or navigation mode and managed lateral guidance. If the error is greater than 3 nautical miles, you can consider that the FM position is not reliable. In such a case, the SOP recommends to use raw data for navigation and to monitor it. You are in flight. Everything is normal, when suddenly On the engine warning display, read the title of the failure. Also notice the check at on both PFD, indicating that there is a difference in the aircraft attitude displayed to the pilots. There is no ECAM page associated with the ADIRS, so the cruise page remains on the system display. The attitude cross-check demanded by the ECAM procedure is carried out by comparing the PFD attitudes with that of the standby horizon. In this example, the first officer PFD, which shows a different attitude to that given by the captain's PFD and the standby horizon, is likely to be the one at fault. Having identified which PFD is giving the incorrect attitude display, the AT heading switch should be selected to that side. In this case, the switch must be selected to the First Officer 3 position. The pilot flying will ask you to perform the ECAM actions. You, as pilot non-flying, read and perform ECAM actions. Perform ECAM action. IR3 is now supplying the First Officer side. The aircraft attitude on the First Officer PFD is back to normal. Check at indications have disappeared. Clear navigation. Notice that as the status page is empty, the status reminder is not displayed, so everything is normal. ECAM action completed. We will continue with an ADR1 fault, which normally supplies ATC1. Let's assume you are the pilot non-flying. You are in flight, in cruise, and everything is normal. On the engine warning display, read the title of the failure. Notice on the PFD, the speed, altitude, Mach and barometric indications are lost. The procedure requests you to switch the air data switch to the captain position. The pilot flying will ask you to perform the ECAM actions. You, as pilot non-flying, read and perform ECAM actions. Perform ECAM action. By switching the air data switch to Captain 3, ADR3 supplies the captain's PFD, ND and the DDRMI instead of the faulty ADR1. ADR1 has to be switched off. Continue ECAM action. No, click on the ADR1 push-button switch. ADR1 is now off, which has led to a ground proximity warning system fault. After review and confirmation from the pilot flying, clear navigation. Ground proximity warning system has to be switched off. Continue ECAM action. After review and confirmation from the pilot flying, clear to see the status page. Clear navigation. The status page is displayed for review. A green message advises us that the approach capability is degraded to Cat 3 single only. You can see in the Inoperative Systems column that ADR1 and Cat3 Dual are now inoperative. The ground proximity warning system is also unavailable due to the ADR1 fault. After confirmation from the pilot flying, you can clear the status page. Clear the status page. ECAM action completed. Let's now see a demonstration of an in-flight radio altimeter abnormality. You are the pilot non-flying. You are in descent. Everything is back to normal. On the engine warning display, read the title of the failure. Observe that the radio height is now measured by radio altimeter 2. As there is no associated procedure, after review and confirmation from the pilot flying, clear navigation. The status page is displayed, showing inoperative systems and aircraft information. With only one RA, Cat3 is unavailable, and the failure of RA1 causes the loss of the ground proximity warning system. After review and confirmation from the pilot flying, clear status. You are flying an approach manually, with RA1 still faulty. On the engine warning display, read the title of the failure. As there is no associated procedure, after review and confirmation from the pilot flying, clear navigation. The status page is displayed, showing inoperative systems and aircraft information. With both RAs faulty, both autopilots are lost in approach, as well as the auto callouts. After review and confirmation from the pilot flying, clear status. The ECAM system display automatically reverts to the cruise page, and the status reminder is displayed on the engine warning display. The first part of the navigation abnormal operation is now complete. You will now study how to tune nav aids using the RMPs. Let's assume you are the pilot non-flying in cruise. You have just lost both FMGCs. As shown on MCDUs and by the red Map Not Avail on the ND, a double FMGC failure has occurred. Here we will focus on the navigation, so we will consider that all the actions concerning the other systems have been performed. As the MCDUs are no longer available for navigation and nav aid tuning, the only navigation capability remaining is radio aid raw data. For this, we need to use the standby nav aid tuning capability of the RMP. The activation of the standby navigation is achieved by pressing the navigation key on either RMP1 or RMP2. Select Standby Navigation on RMP1. The guard is up. Continue. Select Navigation key on RMP1. The green navigation light illuminates to indicate that RMP1 is now in navigation mode. The navigation mode has been selected for you on RMP2. The green navigation light has illuminated. For nav aid tuning, RMP1 standby navigation keys are associated with VOR DME1 and ADF1, while RMP2 keys are associated with VOR DME2 and ADF2. Either RMP1 or 2 can tune the ILS. To illustrate this, we will tune an ILS. The required standby navigation key can be selected. Select Standby ILS key. The Standby Navigation ILS key is illuminated. The active window is now showing the last memorized ILS frequency, while the Standby CRS window is displaying the last memorized ILS course. Notice also that the selected radio light is now extinguished. We will tune a different ILS. Press the transfer key. The Standby CRS window is now displaying the current ILS frequency. Select ILS frequency 108.9. Press the transfer key. The new ILS frequency is now tuned. We will adjust the course. Select ILS course to 145. No, click on the frequency selected knobs. The new ILS course is now set. The tuned ILS is ready for the approach. The setting of the other nav aids, frequency, course, is done in the same way. Note that if an ADF receiver is selected, pressing on the BFO key will activate the beat frequency oscillator. Note, when an RMP is used to tune an ILS DME, the PFD does not display the DME distance. To use the RMP for communication frequency change, you must select the appropriate COM key, i.e. VHF1. The standby navigation mode remains active, and any nav aids using standby navigation mode remain tuned. We will now review some indications we did not have the opportunity to see when performing the previous procedures. We will see first an ATC unit failure. The code display goes blank and the ATC fail light illuminates when the selected transponder has failed, in this example, transponder 1. System operation may be recovered by selecting the other transponder. Select transponder 2. With the selection of the second transponder, the code reappears in the display and the ATC fail light extinguishes. The ATC TCAS unit is again fully operational. We will continue with the weather radar failure messages. In case of any failure, a message appears on the ND. Amber for a radar performance degradation, red when no image is available. The next faulty system is the TCAS. In case of TCAS failure, a TCAS fault is displayed on the engine warning display and TCAS red flags appear on both PFD and ND. Note that there is neither a warning light nor an oral warning. We will now study the DDRMI flags. In case of failure, specific flags can appear on the DDRMI. In case of RMI internal failure or power supply loss, all flags are shown. The abnormal operations are now complete.